All right, so welcome to our exam two review session. Notice that I have exactly 3 bullets up there regarding the entire list of topics that we're going to be doing for this review. It's a lot of stuff. The second bullet encases a lot of stuff, but that's pretty much what we're going to be spending a lot of time talking about after Suzuki and Heck, of course. Okay, so yeah, without further ado, let's go ahead and get started with our discussion on our palladium cross-coupling reactions, that being our Suzuki coupling and our Heck coupling. Okay, so for our palladium cross-coupling reaction, Suzuki coupling, remember that the whole premise of that is that you're going to be taking 2 groups that are vinyl or sp2 and you're going to be putting them together through the use of some palladium, catalyst, base, and heat. Okay, there always is there could be like some sort of variation as to what you actually use for that, but you'll be using palladium or in some cases nickel to some extent. Okay, so what we're going to be using is an sp2 or a vinyl boronic acid or ester. So that will either look like, do this color, either like this or like this, right? And then sometimes you might see some boronic esters that are a little more crazy, like for example, this little 5-membered ring guy right here. Okay, so there could be many different possibilities that you can use for this. Okay, then you have your sp2 or vinyl organohalide or triflate, right? So remember that your organohalide or triflate ideally is a good leaving group. Triflates are a pretty good example of good leaving groups. They actually look like this. Okay, so you have a CF3 for a very deactivated ring, and this can be abbreviated as OTF for O-triflate. Okay. In addition, you might have your classic leaving group halides, such as iodides, bromides, and chlorides. Okay, and pretty much their capability of reacting is the same as you would expect for a leaving group. Okay, you guys know that iodides are better leaving groups than bromides, so they will be more likely to participate in a Suzuki coupling reaction, much more likely than a chloride. Okay. So some advantages of Suzuki coupling, okay, are that for Suzuki coupling, we are able to easily control our stereochem. Okay, when we say easy stereochem control, that just means that we are able to freely go and we're able to freely go and whatever the stereochem of your starting materials are will be the same stereochem for your products. Okay, so let's take a look at that. Let me move this guy a little more down. All right, so let's say we have some sort of a phenyl bromide, and then we have something like this reacting with it. Okay, so reacting both of these together in solution with all the reagents that I have listed above, or a variation of that. So it'll be like PDPPH4, triethylamine, and heat. Then you want to make sure that you're going and then you're linking those 2 sp2 groups together, right? So a couple things that you do want to be careful with is things like carbon count. So notice that here you have 6 carbons, and then here you have 1, 2, 3, 4, 5 carbons. Okay, so if you're linking 6 carbons and 5 carbons together, that means that you should have 11 carbons in your final product. Okay, and something like this, it's always very, very useful to go and then count your carbons, because you might potentially go and accidentally miss one unintentionally. Okay, so with this, coupling these together, we can use a highlighter to help us out. We put these guys together, and then we put, here, I actually use this color, whatever, this color. Okay, we could put these guys together, and then we could put these guys together. Okay, and then afterwards, our products will have, the carbons from our bromide, up my Apple Pencil. I just charged my Apple Pencil. Come on. Right, I'm sorry. Give me a second. Yeah, so I'm gonna have to let this charge for a little bit. I did have to unplug. But yeah, essentially, if you have 6 carbons and 5 carbons together, putting those two together will give you a total of 11 carbons, with a new bond being made between those two sp2 carbons that had those groups that you had. Okay. Yeah. So that's basically how Suzuki coupling works. And you're gonna see when I go and then share my screen once again that I will now have that the double bond that I'm forming is going to be cis. And the reason why it's cis is because of the fact that the starting material that had the boronic ester was originally cis. Okay, let's try this again. All right. So yeah, we made our new bond over here. And then everything else was just this cis double bond right here. Cool. Likewise, if we had the exact same reagents, but let's say we had a trans boronic ester instead. Then our product would just end up being trans. Cool. Still with 11 carbons. All right. So now understanding that, we can go and then take a look at some of our other palladium coupling reactions, such as HEC. One thing that I will say in terms of the mechanism for Suzuki, the mechanism is not necessary for understanding. Cool. So I did whip up some examples of Suzuki that we'll be doing before we go into our carboxylic acids and derivatives. But you're going to see that the mechanism is not totally necessary. So it's a bit more of a straightforward reaction than the HEC reaction is. The HEC reaction, I'll show you guys also a more complicated example that requires you to actually draw the mechanism to be able to understand the product. Cool. All right, any questions about Suzuki coupling before we move on to HEC? Okay, let's go ahead and move on to our HEC mechanism. So with HEC, we have a little less control over stereochem, but it's no big deal. But in order to understand the transformations, you do need to know the mechanism. So we're going to be going over a simplified, or like the regular version of the mechanism, and then see how the mechanism can vary in more complicated examples. Okay, so for this, I'd say that the big advantage with HEC coupling is that you're able to do more complex transformations based off of the one step of the mechanism that pretty much determines regiochemistry. Okay, so let's go ahead and then take a look at that example, or take a look at that. So for this, we're going to be using an sp2 or vinyl organohalide. I'm not going to leave triflate in here because usually I haven't really seen triflate in here. Okay, but you will have an alkene that usually has a vinyl hydrogen. Okay, the reason why I say usually is because there might be some cases that might be a little more complex, that might not necessarily have the vinyl hydrogen to go and then give you the transformation that you want. Okay, and in that case, that's where the mechanism really becomes important. All right, so for a generic example of a HEC reaction, we can take some sort of a phenylbromide and we can take some sort of or not even a phenylbromide, some sort of a vinyl halide or aryl halide, and then some sort of an alkene, doesn't really have any groups on it, doesn't have any boronic ester or acid, and you can go and add in your ligands necessary to go and then conduct the reaction. Okay, it's either this or a variation. Now, the overall product for this, the major product, ends up looking like this, and like the corresponding diastereomer as well. Okay, so one of these will be your major product, and does anyone know what the major product might be in this case? Fifty-fifty chance, guys.
Would it be the E isomer?
The E isomer, right? And why is that?
Because it's more stable.
Yep.
Less steric hindrance.
Yep, less steric hindrance. So this will likely be your major product due to sterics. Cool. So now let's go ahead and then take a look at the mechanism to go and then make that happen. Okay, so for this, okay, so you're going to take your,
I didn't get that.
I really need to disable Siri being randomly activated. Okay, so we're going to take our phenyl bromide or your whatever R bromide you have. Take your palladium, and you don't have to show like the L2 or like the two ligands that like I've had attached to it previously. You can if you want, but essentially that palladium goes and then just inserts itself in between the phenyl and the bromide. Okay, so that's going to be the preparation of your reagent. Now, like any good mechanism, it's always good to understand what the partial charges are like in this case, right? Particularly whenever you have some sort of an organic group bound to a metal, that organic group is going to receive a partial negative charge where the metal receives a partial positive charge because that metal is oxidized, right? So we can go ahead and then implement that when we actually go and then attack our double bonds. So I'm going to use the double bond that we had from our starting material over here. And I'm going to start off actually by drawing this in the force perspective. This just makes my life a little easier for understanding how the reaction works. All right, now taking this, remember, we need to understand our partial charges for this guy as well. So we have a partial negative, partial positive, partial negative, partial positive. And of course, if we have our alignment like that, then we certainly want to be making sure that we can align our partial charges as we see fit here. Okay, so particularly what you'll be seeing is that this guy will be coming down and then attaching to that partial positive. This guy comes up, kicks off the bromide, and we're going to go and then end up with this intermediate that you see here. Okay, so those are the new bonds that you've made. Now at this point, we're going to be doing what we call a beta hydride elimination, right? I've seen different versions of the mechanism where it acts as a hydride as a proton, but the most common case is when it acts as a hydride. And essentially what you want to do is that you want to be taking one of these hydrogens right here and then rotating it so that way it's syn periplanar with the palladium, right? So both next to each other on the same plane, so that way we can go and then perform that elimination. All right, so this isn't a new step. I'm just gonna go and then rotate. And I end up, when I rotate, let's say I go and then I rotate this guy over here.
Sorry, on what side rotate?
This side right here. Okay. So we can have the phenyl come down. and that other proton go to the back. Okay, which one or which proton we choose does not matter. I mean, there will be one major product at the end, but both hydrogens are totally capable of that elimination. All right, now once we have that, we can go ahead and then perform that elimination. This acts as a hydride, so you want to go ahead and then send your electrons up like this, and then this will come down to go and then form your double bond. And thus, dang it, you end up with your final product, which ends up looking like this, okay? So that's one of the products, and then of course, if you were to go and then eliminate this hydrogen, what is going on with my? So eliminating the other hydrogen will result in the Z product. Cool. So that's a mechanism for your Heck. Yeah, that's the mechanism for your Heck reaction. Okay, so real quick before I move on to carbonyls, I'm going to go and then show you guys a couple of examples where this can be applied. Any questions on this? All right, I'll give you guys like a couple more seconds to copy that down before I move on.
In general, like, do you determine which one you rotate based on just like which product is more favorable?
Yeah, right. I mean, this one I knew, I mean, just by like observing it that the proton in the back would go and then give you the more favorable product. But in either case, if you're not sure, you would have to go and then show both to see which proton you want to eliminate.
Gotcha.
Okay, so let's go and take a look at some examples that we have here. Okay, so for this top reaction that we have, so we have this big bad boronic ester that we want to go and then react in order to get us to this intermediate. Okay, so are there any ideas as to what we might be using in order to go and then get to that intermediate? So first of all, what part of this corresponds to our starting material? Or what part do you think corresponds to starting material?
The bottom left phenyl.
Yep, the bottom left phenyl, right? Just that one on its own. Okay, so that means that we have to go and then add in this group here somehow. So notice that we're going and then we're making a bond and we still have a halogen left. So what do you think that tells you about the reagent that you're adding it with?
It's dibrominated.
Dibrominated, but there might be like a better option.
We have iodine
Yeah,
and then bromine.
Yeah, and why do you choose iodine?
Because it's a better leaving group.
Yep, so hypothetically, if you were to do something like this, you would want to specify one equivalent of your starting material, or you could just not do that and then specify 0.5 equivalents of your reagent, doesn't matter. And then of course, add in everything that you see here. Cool. So now for your final product, what do you think is the new part that we're adding? Tabor?
A phenyl group with the methyl group attached to it.
Okay, so we're adding in this guy right here. So what kind of reaction might we want to use here, Suzuki or Heck? Or does it not matter?
We'd be using Suzuki since we don't have a double bond to use Heck on.
Right. So if you were to use heck and just add in toluene, you'd get really big problems with regiochemistry here, right? However, if you have your boronic ester or acid already added onto your compound, okay, here's a boronic acid, just change it up. Then you would be able to go in and do a Suzuki just fine. Okay, so here we did a heck, and then here we have a Suzuki. Beautiful. All right, so let's take a look at our next transformation. So for this first step right here, so what do you think in this intermediate corresponds to your starting material? Nicole?
Why would the first one be heck if you're doing a boronic acid?
Yeah, it should be Suzuki.
Okay.
Getting a little ahead of myself here. Yeah, so Suzuki. Cool. So for this one, what part of your starting material would be, or like what part of this comes from your starting material? Loki, you should also specify that this is actually this.
That will be the leaving group as O-tosylate, right?
Mm-hmm.
In that case, so we would be able to make another Suzuki reaction.
Right. So this guy right here. So that's your O triplet. Okay, so it's just the same thing as PHOTF. Okay, so that means that this came from your starting material. So we can go ahead and then add that in. Okay, so that means that here we would have to add in some sort of boronic acid or ester.
Wouldn't we be adding a straight carbon chain?
Yes, well, I am. Would it be sister trans?
It will be cis.
Cis, very good. Yep, just like that. Cool, yeah, so that'll be a Suzuki. All right, and then for the second step, what do you think we might be doing?
Is it heck?
Yep, so this time it actually would be a heck because essentially what you want to do here is insert right over here. But remember that within that step within the heck mechanism, you're actually not going to be preserving the same relative stereochem that you had between the phenyl and the ethyl group that you have there. Okay, so for this, and I'll show how that looks in the mechanism. So you'll be adding in some sort of like a phenyl bromide. And all that stuff to go and then go ahead and then get you that. Okay, so I'm gonna jump to just that point in the mechanism. So where you have okay, yeah, so you're going to be adding in your palladium over here. And your phenyl over here. Oh wait, yeah, that's why. Here we go. I was like looking at the product instead. Okay, and then here you'd want to go and then rotate this carbon right here. to get you this. Then afterwards, that's when you go ahead and then do that elimination. But remember that in the process of doing that, you're gonna go and then kind of like make this ethyl group trans to the, you're gonna make that ethyl group trans to the original phenyl group that you see there. Okay, which is why the stereochem is going to be slightly changed. So yeah, don't just assume. There was a meme on one of the pilot sets 2 weeks ago about this. Make sure that for hex stereochem, you draw up the mechanism to know what the product will look like. Okay, any questions on either of these?
Why was the upper right hand reaction Suzuki again? Sorry.
Because you have a boronic ester.
No. The second step of that one.
Second, oh, so it had to be Suzuki because you wanted to make sure that for your boronic ester, or sorry, for your boronic acid, you needed to have some sort of boronic acid in place. So you go and then enforce that regiochem. Okay, if you didn't have a boronic acid in there, then like your regiochem would be all over the place.
Okay. So just because
How
like
do you
it's more
take-
reagent selective?
Yeah, right?
Okay.
Was there another question?
How do you pick between the two, like for any given situation?
So you picking between the, you have to pretty much do what I did here and just kind of go and say and ask yourself, do I need specific regiochem? Do I need specific stereochem, etc.? Or is my stereochem going to be flipped or going to be altered somehow? So if there is going to be some sort of alteration based off of the heck mechanism, then you would have to go and then be careful with, and then you might want to go and then use heck. But if you need specific regiochem, then Suzuki might do the job for you. Any other
Okay,
questions?
thank you.
All right, I'm going to go ahead and move into carboxylic acid and derivatives. But to start, before even doing the reactions, I have a little activity. So I have an activity regarding reactivity. Haha, that rhymes. So yeah, I have listed all the types of carbonyls that we have seen here, that we have seen up to this point in this class, in alphabetical order. So we want to go and then use this little chart that I've created here to go and then rank them based off of reactivity. Okay, so let's start off with this top box over here. Which of these carbonyls would you expect to belong in the top box?
Acid-chloride.
And how do we know?
Chloride is just a very good leaving group and
And why is it a good group?
high electronegativity.
It's mostly based off of its size. So electronegativity, yes, but also size. So nucleophile can come in and then do that reaction in order to give you your new functional group. And now the chloride is much happier in solution because it went from being a little larger in the starting material to being now a little smaller with that extra electron. Cool, what's next?
Would it be the ester?
No, not the ester.
The anhydride.
And how do we know? What's the reasoning?
Is that because carboxylate is like a good leaving group?
Excellent. Yep. So whereas the first one was size in the leaving group, next one was the resonance in your leaving group or stability in your leaving group. Okay, particularly if we had something similar to what I drew here. And I had a nucleophile coming in and attacking, boom, boom, boom. Then I got my new group. And then you see here that this leaving group that I just kicked off is resonance stabilized. Cool. All right, now what? Anyone?
Carboxylic acid?
No.
Aldehyde?
Yes, aldehyde. And aldehydes, the reason for that is that you don't really have a good leaving group there, but you are relatively unhindered. Okay, and then what do you think comes after the aldehyde?
Ketone.
Yep, the ketone, where the ketone is slightly more hindered. And then we have two groups that have the same relative reactivity. So what do you think those two groups are?
Is it the ester and amide?
Not amide.
Ester and carboxylic acid?
Carboxylic acid, very good. And what do you think puts them here in this part of the chart?
Is it the residence in the pi system between in the carboxylic acid between the oxygen and the OH, and then in the ester it'd also be the oxygen and the OR.
Yep. So here I like to say that you have okay resonance stabilization. The reason why I say it's okay is because when you go and then you draw your resonance structures, okay, you have one oxygen that has a negative charge, which is happy, but then one oxygen has a positive charge, which is sad. Okay, so it makes it less reactive because of the resonance, but a little more reactive than something else, because of that that resonance distribution. So what do you think is next? What are our next two that are tied?
Amide and nitrile?
Yep. So amide and nitrile, they have it's been debated. I've seen answers for both. I've seen nitrile is maybe slightly more reactive than amide, but in general, they're pretty comparable. So we have the nitrile and the amide leaving our carboxylate at the end, and all of these are really, really happy with the resonance. Okay. Great resonance stabilization. And then, so particularly for the amide, what we're looking at okay, so we have a negative charge on oxygen, which is electronegative, and we have a positive charge on nitrogen, which is electronegative. Both of those are happy, and then the carboxylate either resonance structure has a negative charge on oxygen. So they both have really good resonance stabilization based off of their electronegativities. Cool. So yeah, that's really good for understanding the relative reactivity for each of these. Are there any questions of these before we move on to our reactions of carboxylic acid derivatives? Okay, so what I'm going to be showing, I'm going to be going down this list. Actually, I'm going to be going pretty much up the list of reactivity. So I'm going to start off with carboxylate, and I'm going to be moving upwards. So I'll be covering everything except for these two, which I'll be leaving for the next part of the review session, which Molly will be talking to you guys about. Okay, but we're going to be starting off with our carboxylate. Okay, so the synthesis of carboxylates is actually very straightforward. It's more of a useful intermediate than anything. Cool. So in order to synthesize a carboxylate, you'd likely be starting off with carboxylic acid. And what do you think you would be doing in order to go and then react and then form a carboxylate?
Just add in base.
Yep, so add a base. Doesn't have to be a super strong base. You can add in like sodium hydroxide. Or just base in general. And you're gonna go and then deprotonate to end up with a carboxylate. Okay, nothing really too nothing really too out of this world. All right, so that is your main carboxylate synthesis. Now we're gonna go on and then move on to our amide and nitrile synthesis. So I'll start off with amides first. All right, so for our amide synthesis, they should say carboxylate synthesis too. So do any of you guys recognize a reaction that we can use to synthesize amides?
DCC with NH3 on carboxylic acid.
Absolutely, that works. I have to drop that bond here. Okay, yeah, so that is your DCC coupling. So step 1, DCC, step 2, whatever amine you want to add in order to make whatever amide you want. And then that will look something like this. So let's go over the mechanism for that. Okay, so remember that DCC just looks like this, where CY just represents a cyclohexyl group. Okay, so with this mechanism, we're going to be seeing a trend that, if you know me, I personally really like, but you'll have to see it to know exactly which one it is. So first, you want to go and then take the electrons from nitrogen and then have them attack your carboxylic acid in order to deprotonate. And then from here, you end up with a carboxylate, which serves as a pretty good intermediate, pretty good nucleophile for the next step of this mechanism. Now here you want to go ahead and then attack your carbimide like this and send your electrons up that way. And then this go and pretty much concludes the first step of that mechanism. Okay, just the addition of DCC will have you stop there. Now for the next part of this mechanism, what we observe happening is our ammonia adding in. And as always, we're going to go and then get a tetrahedral intermediate. Okay, so then this tetrahedral intermediate, I like drawing a very specific way because we're going to be doing a very specific type of elimination here. Okay, and then we have this really, really pretty type of reaction. You're going to be seeing this a lot. Essentially, what you can do is have this come in and grab this proton. This goes and then forms a double bond here. And then this goes and then kind of like goes and then kicks that off as a separate byproduct. And then you're going to end up with a product that looks like this, which is just the resonance structure of the amide that you're supposed to be forming. Okay, you don't have to draw it as a resonance structure. You can go in and take it straight to like the carbonyl product, but I think with the resonance structure, it makes this look a little prettier. And then the byproduct that you end up forming is your dicyclohexylurea. Cool. And that is your DCC amide synthesis. Any questions on this? Tabor?
Do you think there's any part in this that the professor could throw something in that's unique and it would kind of stop this process or the mechanism, and then we'll have to do something different?
So maybe not for amide synthesis, but you can actually use DCC to synthesize anhydrides as well. You guys haven't learned that, so don't worry about it. But if you're curious, like synthesizing an anhydride with DCC is just a matter of, instead of adding in an amine, you'd be adding in something like an anhydride, or sorry, an anhydride, acetic acid or an acetate or something like that.
Okay.
Mhm.
Thank you.
Cool. Okay. What other ways do we know to synthesize amides?
You can start with an acid chloride and add in 2 equivalents of an amine.
Very good. So use an acid chloride, add in whatever amine you want. And make sure it's either 2 equivalents or you use something like pyridine along with the amine. So or amine and pyridine, which rhymes. Okay, so going and then adding those 2 together. This follows a very simple mechanism, but this is actually a mechanism that's pretty much useful for the Weinreb amide, right? So if you were asked to synthesize the Weinreb amide, you would be using this type of mechanism. But this works for forming any amide as well. Okay, so first step, come in and then attack here. Send your electrons up. Take your second amine, deprotonate here. You end up with a net negative tetrahedral intermediate. And then in the last step, you would just go and then reform this carbonyl and then kick off the chloride. To give you this final amide product, okay? So you form the amide product, and then the byproduct that you end up forming is this ammonium chloride, okay? So if you were to use pyridine, then your byproduct would be pyridinium chloride. Does anyone know why we formed why this is especially important?
Because don't you have to put in like HCl or something in order to suppress the formation of HCl?
So the whole point of this intermediate is that it goes and prevents the buildup of hydrochloric acid. Because what do you think might happen if I have hydrochloric acid in solution?
It will react with the
React
base.
with the
Yep. So you would go and then you would encourage the reverse reaction. So adding in either 2 equivalents of amine or adding in pyridine to soak up that chloride will allow you to go in and push that reaction to completion without, or like pretty minimizing your risk of doing the reverse reaction. Okay. Any questions about amide synthesis before we go on to nitrile synthesis?
the mechanism for the last one, would you be able to like on that first step where the nitrogen attacks the middle, would you be able to attack the middle, send the electrons up, send them back down, and then kick off chloride all in one step, or no?
You can. I've seen him both ways, but I personally like this one better, just because that way you
Okay.
don't. you have like the residence stabilized thing right off the bat.
Gotcha. Thanks.
Okay, nitrile synthesis. So for this nitrile synthesis, I know you guys have synthesized nitriles in the past through a variety of ways. I think the two main ways that you guys have synthesized nitrile, or actually more than two, main ways that you've synthesized nitriles in the past are from SN2 of a KCN of a nitrile or cyanide on a leaving group or on an alkyl halide. You've had cyanohydrin formation. You've had conjugate addition of cyanide. On your alpha beta unsaturated carbonyls. And there was another reaction before what you're about to see here that doesn't involve a carboxylic acid derivative, but is another great way to form a nitrile. Anyone remember what that is?
Sandmeyer's.
Sandmeyer, excellent. Okay, so these are all methods that we have learned previously. Not going to go over them again because that's old exam material, but for cyanohydrins and Sandmeyer and conjugate addition, you can look back to the exam 1 review session in case you forgot how to go about that. The video is online. For nitrile synthesis here, the main new way that we saw was actually dehydration of primary amides. I don't know what's going on with my Apple Pencil here anymore. Probably running out of battery again. Okay, and then for our dehydration of primary amides, essentially the way that this works, start off with your primary amide and then just use thionyl chloride. And then you should go and then end up with your new nitrile products, and the byproducts are going to be sulfur dioxide and hydrochloric acid. So let's go ahead and then take a look at that. So take your electrons from nitrogen, have oxygen come in and attack here, electrons down, and then send them back over here. Then you end up with this intermediate, which you guys already know what I'm about to do. I'm gonna do my favorite little 6-membered elimination. And just for consistency, let me change the arrow colors. And what we're gonna see here is that we form sulfur dioxide, form hydrochloric acid, and then form your carbon-nitrogen triple bond right here. Okay, and then from here, you would just go and then take the leftover chloride from earlier that you kicked off, deprotonate, and end up with your nitrile. Cool. Any questions on nitrile synthesis? On the other method that you guys know is with P4O10. I don't think you guys have to know the mechanism or the structure for that, but still very useful synthesis. Any questions on that? All right, next up, I'm going to go and take a look at my synthesis of esters. And there's quite a few. Right. The main way to synthesize an ester that you guys know is from a carboxylic acid. And what I know is that there are two main ways to go ahead and then do this. So your first one is your Fischer esterification. And remember that for Fischer esterification, we start off with your carboxylic acid. You add in an alcohol of some sorts. You add in, can you stop? You add in an acid and heat, and you're gonna go and end up with your final ester products. Okay, and there are many different variations of this Fischer esterification mechanism that you, or like Fischer esterification that you might see, which I'll talk about in a little bit. Okay, so one of the things that you might see for Fischer esterification so first you start off by adding in whatever acid you have. And then next, the alcohol that you have in solution comes in and then attacks right over here in order to give you a tetrahedral intermediate. Okay, the alcohol that you're adding in is probably your solvent, so you have a lot of it, and that's probably going to come in and then deprotonate in order to give you a net neutral intermediate. Then take your acid, protonate that. And then the reason why you want to go and then protonate one of the hydroxyls and not the ether once again is because if you protonated the ether, you would just be going in the reverse direction. Can the ether be protonated? Absolutely. But we're trying to go forward, not go in circles. Okay, so we can get that. Then from here, we form our carbonyl, kick off our water, and we end up with almost our final product. Which all we got to do afterwards is to deprotonate here and yield our final ester. Okay, and then our byproduct here is water. Now, I do also want to note that this Fischer esterification is also possible from an ester as well. Okay, so let's say, for example, oh, right when I ended that, my Apple Pencil died. Okay, so I'm going to quickly unplug this. So take a quick screenshot if you want to. 5, 4, 3, 2, 1. I guess while we're waiting for my Apple Pencil to quickly charge, I will stop for a quick minute of any questions about anything I've said so far.
Is this like one of those reactions where you want to protonate the double bonded oxygen before you attack the middle?
Yeah. And how would we know that that's what we want to do first?
Oh, because it pushes the electrons up to make that OH group on top?
Yeah, because we're working in acidic conditions, right? So you want to make sure that you are minimizing any anions you have in solution.
Got it. Okay. Okay.
Any other questions? Okay, yeah, so yeah, pretty much while I wait a few more seconds. The next thing I'm showing you is transesterification. Transesterification, people tend to overlook, but it is certainly possible. That is where you take an ester of some sort and you convert it to another ester. So you can convert like a methyl ester to an ethyl ester. I'll show you guys an example in 5, 4, 3, 2, 1. All right. There we go. All right, yeah, so essentially I want to quickly just get this out of the way. So let's say I wanted to go and then convert that into an ethyl ester. Instead of converting it back to the carboxylic acid, I could just go and then convert it straight through a Fischer esterification mechanism. So that means that you could do Fischer esterification on either carboxylic acids or on esters. Cool. There's another more simple but sometimes less effective way of doing this. And this is just by generating the carboxylate. So from here, what you can do, as we did earlier, go and then generate that carboxylate. Useful intermediate, as I said earlier. And then afterwards, we can go and then bring in some sort of like an alkyl halide to go and then attack here, hence giving us the ester product. Okay, so two different ways, two different, or like one is one step, one is two steps. Either of them works pretty well though. Cool.
Just a quick question about that. That's just SN2?
Yeah, SN2. Okay, and then there is another way which involves an acid chloride. And for this, if you want to go and then synthesize an alcohol, you can go and then, synthesize an ester, you can go and then take some sort of an alcohol and pyridine for the same reason that we use it for the amide synthesis, and end up with an ester. Well, same exact mechanism as for the amide, so you can go and then take that amide mechanism and then translate that into that. Any questions on that?
You said this was the amide mechanism, right?
Yeah, same exact as the amide mechanism on acid chlorides. Okay, so now let's talk a little bit about carboxylic acid synthesis, and there's a lot. Okay, so for your carboxylic acid synthesis, we've seen many different ways of doing this up to now. Okay, one of them was your so let's take a look at what we've seen. One of them is your carboxylation. Sorry, oxidation, my bad. Using Jones from either a primary alcohol or from an aldehyde. Okay. Other method was Baeyer-Villiger on an aldehyde. As you see here. Okay, third method would have been doing oxidative ozonolysis on alkenes. So let's say I had ozonolysis first step is the same. Second step using oxidative workup. And then that'll go and then yield 2 carboxylic acids. Okay, another thing that you could have possibly done is start off with an alkyne, right? And then do step 1, ozonolysis at -78 degrees Celsius. Step 2, water. So either oxidative ozonolysis of alkenes or ozonolysis of alkynes will go and then give you carboxylic acids. Another one is, if you guys recall from last exam, if you guys had some sort of a benzene that had at least one proton in the benzylic position, you could have used KMNO4 or Na2Cr2O7 in order to go and then give you the carboxylic acid. And then another one, which is kind of from last exam, but you might have not been too familiar with, is your carboxylation of Grignard reagents. Okay, and that pretty much consists of first using carbon dioxide. Okay, essentially to go and then attack here. And then using acid water to go and then neutralize your carboxylic acid. And then the last method, which is kind of just like an umbrella term, that is going to be your hydrolysis of carboxylic acid derivatives. Okay, so pretty much any carboxylic acid derivative can go and then be hydrolyzed into the, or can be oxidized into the carboxylic acid just by adding in water or some sort of variation of water. Okay, so I'll show you guys a bunch of examples of it. I'll only draw the mechanism for a couple because a lot of it is pretty much the same. So for a carboxylic acid synthesis, if I have an acid chloride, just adding in neutral water, because acid chlorides are so reactive, we'll go and then give you the carboxylic acid derivative just fine. Acid anhydrides, adding in water or even acidic water, we'll go and then give you two carboxylic acids. Okay. Next, aldehydes and ketones are not really direct or slash, like we've already gone and covered some of the methods over here. Let's see, for what am I? Okay. For esters, that's your saponification. You could do it either in acidic or basic conditions. Okay, in acidic conditions, it's just acid water, but like it's more common in basic. So just an FYI. Okay, the mechanism for this. Take these electrons, send them over here, up, down, kick off the alkoxide. And then afterwards, you can go and then take the alkoxide and totally against your will. Remember, you have something basic and something acidic in solution. It's going to go ahead and then deprotonate. Okay, this step has to happen because of that KEQ there. Okay, but in order to quench it, you could just go and then add in acid water. And that goes and then gets the job done just fine. Same way that we've seen it before. Cool. That's that. Then we also have our hydrolysis of nitriles and amides. So this is the other mechanism I wanted to show you. And both of these will collapse under acid water. Okay. So now here, the mechanism for this. My iPad is frozen. There we go. Yeah, so the mechanism for this. And I'm only going to show the nitrile one because the nitrile one low-key already involves the amide. As always, protonate the more electronegative atom. Then go and then add in water. All right, and then afterwards, our water can kind of come in and then deprotonate over here. I know Falzone actually kind of likes to show this as like a termolecular step, so I'll actually do it how Falzone does it. Okay, and that is that he goes and then grabs this, and then this will grab this in order to go and then get you to this intermediate. All right, and then from here, you can actually go and, here, let me actually, yeah, that's fine. Yeah, from here you can go ahead and then take your water, add in right over here. Okay, do the same thing you did earlier. Add water. Then do this in order to go and then give us this guy, which is a good leaving group, right? That positively charged ammonia. Then afterwards, you can go, then reform your carbonyl, pick off your good leaving group. And then finally, in the last step, likely ammonia will be coming in and then deprotonating in order to give you the carboxylic acid. Cool. And then the amide hydrolysis is very, very similar. It's pretty much like half of this mechanism if you really think about it. Cool. And then these are pretty much all your main hydrolyses. Any questions before we move on? All right, I just want to quickly wrap up my section by talking quickly about your acid chloride synthesis and your acid anhydride synthesis. Okay, so for acid anhydrides, you can either make acyclic or cyclic anhydrides. For acyclic anhydrides, I mean, many different ways to do it, but the most common way that you might see for this is taking a carboxylic acid, making it into the carboxylate as we did earlier. And then bringing in some sort of an acid chloride. So something like this, where you go and then form a tetrahedral intermediate, collapse it, kick off your chloride. And then you end up with your acid anhydride, okay? So that's the acyclic form, but there is a form that you could do it in a cyclic manner. And that essentially is going and then taking your acid anhydride, reacting it with acetic anhydride, or yeah, acid anhydride, or like acetic anhydride here, and reacting it in order to go and then form this cyclic anhydride. All right, the way that this works over here is that this will come in, up, down, kick this off. So you go and particularly attack at that position because of the fact that it's resonance stabilized, right? If you were to go and then attack with the other hydroxide, then you would lose that resonance. And then from here, we can go on and then attack right here. Okay, that's now an activated carbonyl. And at this point, we've gone ahead and then formed this nice little intermediate. All right, and then from here, the acetic acid that you just formed can go and then deprotonate. Then reprotonate this carbonyl. Then collapse that alcohol. Kick this off as acetic acid. And then to get from here to your final product, just go and then deprotonate in order to get to that final acid anhydride. Cool. Just for time, I'm going to leave this up for like a couple more seconds, and then I'm going to go straight to the acid chloride synthesis. Very simple mechanism, but also one that you should be very, very acquainted with. Cool. All right. So now for our acid chloride synthesis. For that one, you start off with a carboxylic acid. Use thionyl chloride. Then you end up with your acid chloride. Okay, the mechanism for this very similar to the dehydration of amides mechanism initially, where you go and then you take this top carbonyl and cycle those electrons across. Oops, sorry. Send your electrons up and then kick them off. Remember, again, we attack there because of the fact that we want the resonance stabilized intermediate. Attack with the hydroxyl and see in that case how you don't get that resonance stabilized intermediate. Next, your chloride comes in and then attacks. Then you end up with this intermediate. Okay, and then in typical Juan's favorite fashion, you can go ahead and form sulfur dioxide, form hydrochloric acid, and then form your carbonyl, all in one step just by doing that 6-membered elimination. And then that is how you form your acid chloride. That is your main way for doing so. All right, cool. If you have any questions about anything I talked about in my section, you guys are welcome to DM me in the chat. But at this time, I would like to turn it over to Molly so we can go ahead and start on our discussion on more stuff. Cool. So thanks, everyone.
Cool. Hi guys. I'm gonna go ahead and get started. Cool. So we'll just go ahead and get started on ketone synthesis. And so just as a reminder, you guys have already covered a lot of old reactions that form ketones. So I'll go through just like a couple that Falzone really enjoys, but like definitely make sure you brush up on some old material because those could always be really helpful during your synthesis problems. So just for example, one of the common ones that we see is going to be ozonolysis. So if we just like have something with a double bond, we can go ahead and splice it into a ketone. So yeah, that one's pretty common to see still. And then another old reaction that you guys had was Friedel-Crafts acylation. So remember, those ones are going to be your aromatic ones. So you'll have your benzene, and then you'll go ahead and add your acyl chloride. And then your workup. And that will also give you some ketone. Cool. And so a little bit more on the newer information. We also have your Grignard reagents. So one example is if you're starting from an aldehyde, you can go ahead and use one of your Grignards. To create your alcohol. And then don't forget that we also have PCC or Jones, depending on what you're doing, to oxidize your in order to oxidize your alcohol up to a ketone. Okay. And you can also do your Grignards off of carboxylic acids. And so in this case, we just want to remember that we'll need to use two equivalents because we do have this acidic hydrogen right there. And so our first equivalent will go ahead and deprotonate, and then we'll have our second equivalent actually attack the carbonyl position. Okay. Any questions so far? All right, so then closer to the current information that we have on this exam, we also found 3 new reactions that can also give us ketones. And so first up, we have our Weinrebs. So for Weinreb, we're gonna go ahead and get started with an acid chloride. And then using our Weinreb reagent, with pyridine and 0 degrees Celsius, we'll go ahead and change this acid chloride into our Weinreb amide. And then after we form this Weinreb amide, we can go ahead and react it with our Grignard reagent at -78 degrees with our workup. And then this will go ahead and replace that amide portion with your ketone. And just something to note, you have to run this at -78, otherwise you'll overadd. And so if you're overadding, instead of stopping at that ketone, you're going to go ahead and push it to a tertiary alcohol. Okay. Another reaction that we have that we can use to create a ketones is the Jenner-Posner reaction. So with Jenner-Posner, instead, we're going to start with a carboxylic acid. And then we have our reagent that's 5 equivalents of R2 Cooley with LiCN with ET2O and your workup. And then this guy will just give you your ketone again. And then lastly, you might also see Gilman reagents. And so in this case, you're starting again from your acid chloride. And then you'll use R2 Cooley at -78 with your workup. And again, we get our ketone. So these are like just a few of the reactions that you can use to create ketones. So generally when I'm approaching synthesis problems, I really look at what starting material I have, and that will help me determine if I should use like Weinreb versus Jenner-Posner. Of course, we can switch between like carboxylic acids and acid chlorides. So really looking at what you have in your starting material will be beneficial in determining what reaction you want to go. Okay. So any questions on ketone synthesis?
For the Jenner-Posner, oh, actually, never mind. I forgot.
Okay, yeah, no worries. Okay, then next we're gonna switch and do some amine synthesis. Amine, yeah.
Actually, sorry, I had a question about the above stuff. So for the Gilman and the Weinreb, it seems like they sort of do the same thing, except Weinreb has more steps in it. So like, if we were doing synthesis, could we use Weinreb since it's like a better yield, even though it's more steps than using Gilman?
Yeah, I would consider Weinreb as kind of just one step, because when you're creating that Weinreb amide, that's like your intermediate that like progresses this reaction. So I guess like if you're worried about whether or not your synthesis will have too many steps and they'll like take off questions for like longer syntheses, I wouldn't be concerned about it for Weinreb. I think it's a really good option. Yeah, did that answer your question?
Okay, so just consider Weinreb as one step then?
Yeah, yeah.
Okay, cool, thank you.
Okay, any other questions? Okay, now let's do amines. So we have 2 major rearrangements that we've learned for this section. So the first one that we'll go over is the Hoffman rearrangement. And so in this reaction, we're gonna start from your primary amide. And then your reagents will be NaOH and Br2 with water. And then your products will include your primary amine, as well as a byproduct of carbon dioxide. Okay, so I'm just gonna walk through the mechanism for this one. Yeah, so we're gonna start with our amide. And then given we're under basic conditions with the NaOH, we'll go ahead and deprotonate. Once we get here, we'll use our BR and attack that. To get to this intermediate. And then we'll go ahead and deprotonate again. Okay. And then at this step, we're going to draw the resonance structure. So these electrons will pop down and go ahead and form a resonance structure that has the negative charge on the oxygen instead. Once we're here, we have kind of like a methyl shift, like when we were doing those in the first semester. And so these electrons on the oxygen will come down. Your R group on the end will go ahead and shift over to attack our nitrogen, which will kick off the BR leaving group. And so once we have this, we can draw a structure like that, which is called your isocyanate. Okay. Whatever, I don't care. Once we have that, our water will go ahead and come in to attack the carbon and send those electrons up to the oxygen. And so we'll go ahead and have and then we'll go ahead and deprotonate, oops. Okay. And then at this step, we're gonna send these electrons back down to reform a carbonyl. And then we'll push these electrons out to grab a hydrogen. Okay. And then we'll go ahead and do the same thing once more so that we can grab another hydrogen. And once we get there, we have gotten to our two products. So we have our carbon dioxide on the left, and then also the primary amine with the R group shifted. Okay, I'm gonna leave this up for a little bit longer in case you're still writing, but are there any questions so far? Okay, chill. I'll give it just like a couple more seconds. Okay, let's keep going then. All right, next we have another rearrangement. So this one is our courteous rearrangement. And so for courteous, we're going to start with an acid chloride. And then we use our sodium azide, which is just NaN3 with water. And that will go ahead and give us our primary amine again, but this time with byproducts of N2 and CO2. Okay, and again, I'll walk through the mechanism for this one. So starting with our acid chloride, we can use a resonance form of the sodium azide that will look like this. And they will attack our carbonyl, send those electrons around and kick off our leaving group. And then similar to what we had to do for Hoffman, we're gonna do another resonance form of this intermediate. And so that will go ahead and give us this one. Okay. And then at this position, we're gonna do another of those migratory like rearrangements. So these electrons on nitrogen will come down to form a double bond. Our R group on this side will come around to attack that nitrogen and kick off our leaving group of N2. And so we return to our isocyanate. Sorry, I realized I wasn't writing R. It's fine. So we have our isocyanate, and at this position, we got our byproduct of N2 as well. Following that, we'll go ahead and protonate our nitrogen. When water comes into attack, that'll attack the carbon and send those electrons back. And then once we get here, more water will come in to deprotonate and send those electrons down. And then we'll have one more equivalent of water come in to do it once more. That forms our carbon-oxygen double bond. And then this nitrogen-carbon bond will come out to grab a hydrogen. And that collapse will give us our CO2 product, as well as our primary amine. Okay, sorry, the water was floating. Yeah, okay. I'll leave that up again if you're working on it. Are there any questions on those two syntheses or mechanisms?
Could you scroll down a bit, please?
Do you want to see the first one as well? Okay.
Yes, please. Could we also see the first one?
Okay, it's like super. Let me. Okay, I'll hold.
It's okay. You can just go to the second one. You just
okay. Well, I'll leave it on Hoffman for a second. If you want to take a screenshot, like do it now. Okay, 3, 2, 1. And then here's the Curtius. Yeah, thanks, Sam. Okay. Any other questions or comments?
Sorry, for the Curtius, where's the H plus coming from?
So honestly, that could be just like from water. Yeah, it'll just be in the solution.
Got it.
And just like as a comment, Curtius is like very common following a carboxylic acid. So Juan showed you the mechanism earlier to transfer a carboxylic acid into an acid chloride. And so that's something that is pretty common. And I think we had it on the last pilot problem set if you like want to see an example. Okay. All right, now we're gonna switch topics and go into hydride reductions. So we have a few. I'm just going to quickly list them out and then we'll go ahead and do them in order. So we have NaBH4, LiAlH4, also known as LAH, and then NaBH3CN. And this one, you can use that, or H2PDC will do the same thing, which we'll see in a second. We also have dibol or dibla or whatever you want to call it. It's also abbreviated as DIBAH. And then we also have TBLA. Okay. So starting with NaBH4, this one will give you, so if we start with the ketone or aldehyde, using NaBH4, we'll go ahead and reduce it down to an alcohol. Okay. And then And then another thing that NaBH4 is able to do is go from an acid chloride and then also give us our alcohol. So on like a bigger picture, it's one of the weaker hydride reductions that you can do. In contrast, LAH is one of our stronger ones, as in it's very strong. And so this guy, if we're starting with a ketone or an aldehyde, it will also give us our alcohol, but it also has a lot of other applications. So I'll run through a few of them really fast. So if we start from a carboxylic acid, we can also use LAH to get down to an alcohol. It can do work on acid anhydrides. And give us two of these alcohols, like two equivalents, depending on what R groups you have, of course. We also do the same thing on esters. And so this one will give you your first alcohol and then whatever R group you have as well, like right there. Okay. Additionally, it can work on amides. To give you your amine. And then it also works on nitriles. To give you your amine. Okay, cool. Yeah, LAH is like pretty cool. They can do a lot. Okay, wait, okay. I'll stay on that for just a second.
So for the carboxylic acid becoming the alcohol, it's the double bonded O that becomes the OH, right?
Yes.
Okay, and then the OH just becomes like a water.
Yep.
Okay, thank you.
Yeah, exactly. Okay. Any other questions? Okay. So then next is NABH3CN. So this guy's pretty cool. It will turn your imine to your amine. And as like a side note, this can also work with H2PDC. Okay. And then another special one is dibla or dibol. And so the structure of this, which you may see, so it's like just like something good to know, is this guy. Looks like a bat. There's even a head. Okay, and so this guy specializes on esters, amides, sorry, and nitriles, and all of those three types will go down to your aldehyde. So with your ester, these will go down to your aldehyde, your amide, will also become an aldehyde, and then finally your nitrile as well. Okay. And dibol will also work on ketones, and these will become alcohols. Sorry, that's a ketone. And then another key thing to note is that, at least for these top three, especially because they don't go down to an alcohol, but if you don't do it at -78, then it will go all the way down to your alcohol. So if not run at -78 degrees Celsius, you will instead go down to your alcohol. Okay. And then finally, we also have TBLA. So this guy's structure is LA. Just like for completeness. And then TBLA will specialize on acid chlorides. And then these ones will also go down to your aldehyde. So yeah. Good. Yes, that was a very long list of all of the hydride reductions that you might, or most of the hydride reductions that you might be able to see. Are there any questions on those? Okay.
Wait, does TBLA only reduce the acid chloride, or like can it do the stuff dibol does?
No, Tibla is quite weak. It will only do the acid chloride. And like, remember that acid chlorides are your most reactive. So given that it's only able to work on your most reactive, like carboxylic acid derivative, Tibla is one of the weaker hydride reductions that you would do.
Thank you.
Yeah. Tabor, do you have a question?
Yeah, when you're using LAH on a nitrile, I saw that it's just like a C triple bond into an N. If there was an R group attached to the left side, would the amine have that R group attached to it?
Yes, but to like the other side.
Okay, thank you.
Oh, sorry, it's not. Oh, yeah, it did load. Okay, cool. Yeah. Any other questions? Okay. Was there anything any of the pilot leaders wanted to add? Okay. Well, thanks. In that case, that's all we had for you guys today. Wow, we managed to end 10 minutes early too, but yeah, so have fun in pilot this week and good luck on your exam. Sam will send out the recording after we finish. And yeah, let us know if you have any questions. Bye, guys.